What if everything you see around you, the room you're in, the sky above, even the vast expanse of the cosmos, is just one layer of a much grander reality? Picture our universe as a single page in an infinite book, with countless other pages hidden just beyond our perception. This isn't science fiction. It's one of the most mind-bending possibilities explored by string theory, a framework that suggests our reality might be woven from tiny, vibrating strings of energy. And if that's true, it means there could be entire dimensions folded into the fabric of existence. Dimensions we can't see or touch, but that might hold the keys to understanding everything from black holes to the birth of the universe itself. Think of it like this. Imagine a piece of paper. To a tiny ant crawling across its surface, the paper is a flat, two-dimensional world. But to us, it's obvious there's a third dimension. The thickness of the paper, so subtle it's almost invisible. Now, what if our universe is like that paper, and we're the ants, completely unaware of the higher dimensions curling around us? String theory proposes that these hidden dimensions aren't just mathematical quirks. They could be real, physical spaces where the rules of reality are entirely different. Some theories even suggest that our entire universe might be a hologram, a projection from a higher dimensional surface, like a shadow cast by a flickering flame. This is where things get truly fascinating. If these extra dimensions exist, they could explain some of the deepest mysteries of physics, like why gravity is so weak compared to other forces, or how particles can behave in ways that defy classical logic. They might even hold the answer to whether parallel universes are real, floating like bubbles in a cosmic foam just beyond our reach. Over the course of this journey, we'll unravel these ideas step by step, exploring how string theory reshapes our understanding of space, time, and the very nature of existence. By the end, you'll see the universe and your place in it in a whole new light. So buckle up, because we're about to dive into the hidden layers of reality, where the boundaries of science and imagination blur into something extraordinary. We live our entire lives navigating 3 dimensions: length, width, and height so effortlessly that we rarely stop to think about what a dimension actually is. At its core, a dimension is simply a direction something can move or exist in. Picture a ball tossed into the air. It moves side to side, forward and backward, up and down. That's our everyday 3-dimensional reality. But what if there's a 4th direction, one we can't perceive? That's where things get wild. To wrap our heads around this, let's take a trip to Flatland, a famous thought experiment where beings live in a 2-dimensional world. To them, left, right, forward, and backward are all they know. Up and down don't even register. If a 3-dimensional object, like a sphere, passed through their flat universe, it would appear as a dot that grows into a circle before shrinking back to nothing. They'd have no way to comprehend the full shape, just as we might struggle to grasp a 4-dimensional object moving through our world. Theoretical physics treats dimensions differently than our everyday experience. Instead of just directions in space, they're mathematical frameworks that shape how particles interact, how forces like gravity behave, and even how time flows. Some versions of string theory propose up to 10 or 11 dimensions, all curled up so tightly that we'd never notice them. Like a garden hose viewed from a distance, it looks like a 1-dimensional line, but up close you see its full cylindrical form. These hidden dimensions aren't just abstract ideas. They could solve real cosmic puzzles. For instance, gravity's puzzling weakness compared to other forces might make sense if it's leaking into extra dimensions we can't detect. Or consider how particles seem to teleport in quantum mechanics. Maybe they're dipping into higher dimensions and reappearing elsewhere in our own. The deeper we dig, the more dimensions stop being just math and start looking like the invisible scaffolding holding reality together. Einstein shattered our understanding of reality when he revealed that space and time aren't separate entities but woven together into a single fabric: space-time. Think of it like a trampoline. Place a heavy object in the center and the fabric bends, causing smaller objects to roll toward it. That's gravity in action, not some mysterious force acting at a distance, but the curvature of space-time itself. This revolutionary idea didn't just redefine physics, it turned time into the fourth dimension, a direction as real as left, right, or up. But here's where it gets even more intriguing. Einstein's equations didn't stop at 4 dimensions. They left the door wide open for more hidden directions curled into the universe's fabric so tightly we'd never notice them. Imagine blowing up a balloon with tiny ants living on its surface. To them, their world is flat, 2-dimensional, but from our perspective, we see the balloon's full 3-dimensional shape. What if our universe is like that balloon, with extra dimensions folded into every point in space, too small for even our most powerful microscopes to detect? String theory takes this idea and runs with it. If the universe's fundamental building blocks aren't particles but tiny, vibrating strings, those strings might need extra dimensions to move in, like guitar strings needing space to vibrate to produce different notes. Some versions of the theory suggest these hidden dimensions could explain why gravity is so bafflingly weak compared to other forces. It might be spreading out into dimensions we can't access, diluting its strength in our observable universe. Yet even with these breakthroughs, glaring mysteries remain. Quantum mechanics, which rules the subatomic world, and general relativity, which governs the cosmos, refuse to play nice. Black holes, where both theories collide, become mathematical nightmares. String theory offers a tantalizing solution, a framework where gravity and quantum forces might finally unite, but it comes at the cost of accepting a reality far stranger than we ever imagined. Could these extra dimensions hold the key? The answer might lie in the echoes of the Big Bang or the ripples of colliding black holes, waiting for us to listen closely enough. At the heart of string theory lies a radical reimagining of reality, one where the universe isn't built from tiny, indivisible dots, but from infinitesimal loops of energy vibrating like the strings of a cosmic violin. These aren't physical strings you could pluck with your fingers. They're unimaginably small, trillions of times tinier than an atom, dancing through the fabric of space-time. Each vibration, each unique resonance, gives rise to the particles we know: electrons, quarks, even the elusive Higgs boson. It's as if the universe is an intricate symphony, with every note corresponding to a different building block of matter. Think of it like tuning a guitar. Pluck one string and you hear a specific pitch, that's an electron. Tighten the string slightly and the vibration changes, producing a different note. Now it's a photon. In this analogy, the laws of physics become the sheet music, dictating how these strings can vibrate and interact. What makes this idea so powerful is its potential to unify all the forces of nature. Gravity, electromagnetism, the strong and weak nuclear forces, they might all emerge from the same underlying melody, just different harmonics of these fundamental strings. But here's where the metaphor deepens. Just as a single violin string can't produce the richness of an entire orchestra, string theory suggests these tiny loops need more than our familiar 4 dimensions to play all the notes required by the universe. The math reveals that for the equations to work, these strings might vibrate in 10 or even 11 dimensions, with the extra ones curled up so tightly they're invisible to us. It's like listening to a song through a wall. You hear the melody, but the full complexity of the instruments is hidden. This elegant framework could solve one of physics' greatest puzzles: why gravity is so staggeringly weak compared to other forces. If gravity's notes are leaking into higher dimensions, diluted across realms we can't perceive, it would explain why a tiny fridge magnet can overpower the entire planet's gravitational pull on a paperclip. Even more tantalizing, string theory hints at a possible connection between the quantum world and the cosmos, offering a path to reconcile Einstein's relativity with the bizarre rules of quantum mechanics. Yet for all its beauty, string theory remains unproven. a symphony waiting for its first live performance. The strings themselves are too small to observe directly with current technology, and the energies needed to test their existence are far beyond what our particle colliders can reach. But that hasn't stopped physicists from exploring the implications, from holographic universes to parallel worlds. Whether string theory is the ultimate theory of everything or just a stepping stone, it's reshaped how we imagine the deepest layers of reality, not as static points, but as a dynamic, vibrating dance of hidden dimensions. String theory doesn't just suggest extra dimensions for the sake of wild speculation. It needs them to make the math work. At first glance, the idea of 10 or 11 dimensions seems outrageous, but when you dive into the equations, it's the only way the numbers add up. Think of it like building a house. If you forget a critical support beam, the whole structure collapses. For string theory, those beams are the hidden dimensions holding the entire framework together. Here's why. The tiny, vibrating strings at the heart of this theory don't just wiggle in the three spatial dimensions we know. To produce all the particles and forces in the universe, they need more room to move, like a dancer who can't perform their full routine in a cramped closet. Early versions of string theory kept hitting dead ends until physicists realized the equations only balanced if they added extra dimensions. In some formulations, that number is 10, 9 of space and 1 of time. Others, like M-theory, push it to 11. Without them, the math spirals into contradictions, and the elegant symphony of vibrations falls apart. But if these dimensions are real, why don't we notice them? That's where compactification comes in. Picture a garden hose stretched across a field. From a distance, it looks like a one-dimensional line, but up close you see its circular cross-section, a second dimension curled into a tiny loop. Similarly, the extra dimensions in string theory could be coiled up billions of times smaller than an atom, far beyond what any microscope could detect. Even the Large Hadron Collider, smashing particles at nearly the speed of light, hasn't found traces of them, though some theories suggest they might hide in the faintest gravitational ripples or quantum anomalies. This isn't just theoretical sleight of hand. Compactification could explain why the universe looks the way it does. Imagine blowing up a balloon with intricate patterns drawn on its surface. At full size, you see every detail, but let the air out and the patterns scrunch into a tiny, crumpled knot. If our observable universe is that inflated balloon, the extra dimensions might be the crumpled parts, invisible yet shaping the physics we experience. Some models even suggest these hidden dimensions aren't static. They could fluctuate, influencing everything from the strength of gravity to the birth of parallel universes. The real magic lies in how these unseen dimensions might unify physics. In our familiar three-dimensional world, gravity behaves differently than electromagnetism or nuclear forces. But in higher dimensions, they could all stem from the same underlying geometry, like shadows cast by a single object under different lights. String theorists once compared it to tuning a radio. The extra dimensions adjust the frequency of the universe, determining which forces and particles emerge in our reality. If we could perceive all 10 or 11 dimensions at once, the fragmented laws of nature might snap into a single, breathtaking equation. Yet for all its elegance, this idea remains controversial. Critics argue that without experimental proof, extra dimensions are just mathematical fiction. But supporters counter that groundbreaking ideas often sound absurd before evidence catches up. Einstein's curved space-time once seemed just as outlandish. Whether string theory's hidden dimensions are real or not, they've already expanded our imagination, revealing how much of the cosmos might still be hiding in plain sight. Imagine the universe as a slice of raisin bread, except in this cosmic loaf, the raisins aren't just fruit, they're entire worlds floating like islands in a higher dimensional dough. That's essentially the idea behind branes, short for membranes, theoretical surfaces where our universe might be anchored. According to some versions of string theory, we're not just living in space-time. we could be stuck to a vast, multidimensional brain like ants on a leaf, oblivious to the larger bulk surrounding us. The bulk is the backstage of reality, an expanse of higher dimensions where brains drift, collide, or even ripple like sheets in the wind. Picture it like this. If our three-dimensional world were a painting, the bulk would be the gallery housing it, with other paintings, parallel universes hanging unseen just inches away. These brains aren't passive backdrops, they're dynamic stages where the laws of physics play out. Some theories suggest the Big Bang itself might have been the shockwave of two brains colliding, igniting our universe into existence like flint striking steel. This raisin bread analogy helps visualize how multiple brains could coexist without interacting. Each raisin, a separate brain, might harbor its own universe with unique physics, forever hidden from ours unless a rare, cataclysmic event sends trembles through the bulk. And just as raisins expand apart as the bread bakes, brains could drift or stretch over time, explaining why we don't bump into alternate versions of ourselves. But why does any of this matter? Because brains might solve one of cosmology's biggest head-scratchers: why gravity seems so feeble compared to other forces. If gravity's influence leaks into the bulk like sound escaping a room while other forces stay glued to our brain, it would explain why a tiny magnet can defy Earth's gravitational pull. Even black holes might be knots in the brain's fabric, their mysteries tied to higher dimensional threads we can't yet tug. The wildest implication: if the bulk is real, there could be entire civilizations living on other brains, their light and gravity forever trapped on their own slice of cosmic bread. We'd never know unless their universe brushed against ours, leaving fingerprints in the static of deep space or the afterglow of the Big Bang. It's a humbling thought that everything we call reality might just be one stage in an infinite multiverse theater, with dimensions beyond our comprehension waiting in the wings. If these extra dimensions are woven into the fabric of reality, why can't we see them, touch them, or even detect them with our most advanced instruments? The answer lies in how they're hidden not behind some cosmic curtain, but coiled up so tightly that they're smaller than the smallest particles we've ever observed. Picture a spider's web glistening with morning dew. From a distance it looks flat, two-dimensional, but zoom in close enough and you'll see the intricate strands forming a complex three-dimensional structure. Now imagine those strands are dimensions curled into loops a billion times tinier than an atom. That's the scale we're dealing with, realms so infinitesimal they slip right past our perception. This idea isn't new. Back in the early 20th century, mathematician Theodore Kaluza and physicist Oscar Klein proposed a radical theory. Electromagnetism and gravity could unite into a single force, but only if the universe had an unseen fourth spatial dimension. Think of it like a telephone wire stretching to the horizon. From afar, it appears as a one-dimensional line, but up close you realize it's a cylinder with a second dimension wrapped around it. Kaluza and Klein suggested that if a dimension were curled this tightly, it would explain why we only experience three. Their work was groundbreaking, but it lacked the framework to explore how these hidden dimensions might shape reality at the quantum level. Modern physics takes this even further. Some theories propose that extra dimensions aren't just tiny, they're warped like a funhouse mirror bending light. Imagine space as a sheet of rubber, stretched thin but distorted by invisible weights. In this scenario, gravity could be stronger in certain regions of these warped dimensions, leaking into our universe in ways we're only beginning to model. This might explain why gravity is so weak compared to other forces. It's not that gravity itself is feeble, but that most of its strength is trapped in these twisted geometries forever beyond our reach. So how do we hunt for something we can't see? Enter the Large Hadron Collider, the most powerful particle smasher ever built. Scientists have theorized that if extra dimensions exist, the energy from proton collisions might, for a split second, create particles that briefly vanish into them, leaving behind telltale gaps in the expected energy patterns. It's like throwing a ball into a room and hearing it bounce, except the ball disappears mid-air, hinting at a hidden doorway. So far, no definitive evidence has emerged, but the search has only just begun. Other experiments, like ultra-precise measurements of gravity at microscopic scales, could reveal subtle deviations from Newton's laws, potential fingerprints of higher dimensions tugging at the fabric of our reality. The implications are staggering. If even one of these theories pans out, it would rewrite our understanding of existence. Dark matter, that mysterious substance making up most of the universe's mass, could be ordinary matter trapped in a parallel brane, invisible yet gravitationally present. The Big Bang might not have been a singular event, but a ripple in the bulk echoing across dimensions. And the laws of physics we take as absolute could just be local bylaws, rules that only apply on our particular slice of cosmic real estate. Yet for all the tantalizing possibilities, the question remains, are we chasing shadows or on the brink of the greatest discovery in human history? The answer might lie in the quiet hum of a particle detector or the arcane scribbles of a mathematician's chalkboard. Until then, these hidden dimensions linger at the edge of our imagination, a reminder that the universe is far stranger and far grander than it seems. What if our universe isn't the only one? What if every decision you've ever made, every path taken or not taken, exists simultaneously in an infinite web of alternate realities? This isn't just the stuff of sci-fi. According to some interpretations of string theory, parallel universes might be as real as the screen you're staring at right now. The key lies in those hidden extra dimensions and the mind-bending behavior of branes, the theoretical surfaces where universes might take shape. Picture two colossal sheets of paper floating in a darkened room. If they brush against each other, the collision releases a burst of energy, a cosmic spark. Now replace those sheets with branes drifting through the higher dimensional bulk. When they collide, the energy could ignite a new Big Bang, birthing an entirely separate universe with its own laws of physics. Our entire cosmos might just be one bubble in a frothing sea of brane collisions, each creating its own isolated reality. Physicists like Max Tegmark have organized these possibilities into a multiverse level system. Level 1 is the simplest, an infinite expanse of space where every possible configuration of matter repeats endlessly. Far beyond our observable horizon, there could be identical copies of Earth, or versions where dinosaurs never went extinct. Level 2 takes it further with bubble universes, each spawned by its own Big Bang, expanding like bubbles in a cosmic champagne glass. These bubbles might have different physical constants, some where gravity is stronger, others where atoms can't even form. Then there's level 3, the quantum multiverse. Here, every time a particle faces a choice like whether to spin left or right, the universe splits in two. One version sees it spin left, the other right. This isn't metaphor. In the many worlds interpretation of quantum mechanics, every possible outcome plays out somewhere, creating branching timelines where you're both a doctor and a rock star, where the Roman Empire never fell, or where life never arose at all. But how does string theory tie in? Those vibrating strings might dictate the rules of each universe. Imagine a piano where every key plays a different set of physical laws. In one universe, the strings vibrate to create strong nuclear forces. In another, they hum gravity into dominance. And branes, they could be the stage where these universes unfold, drifting through higher dimensions like pages in a book we can't see. The most staggering part, if branes can collide once, they can collide again. Our universe might not be unique, just one link in an endless chain of cosmic rebirths, each with its own story. Some theories even suggest that the mysterious dark energy accelerating our universe's expansion could be a sign of another brane looming in the bulk, its gravity subtly tugging at ours. Yet the multiverse remains fiercely debated. Without observable proof, it risks being untestable, more philosophy than physics. but supporters argue that inflation theory, quantum mechanics, and string theory all point toward it. The echoes of colliding branes might linger in the cosmic microwave background, or gravitational waves could reveal wrinkles in space-time from a neighboring universe. Whether these ideas hold up or not, they force us to confront a humbling truth. Reality might be vaster, stranger, and more interconnected than we ever dreamed. Quantum entanglement is one of the most bizarre phenomena in physics, two particles separated by vast distances instantly influencing each other, as if they're dancing to some hidden cosmic rhythm. Einstein famously called it spooky action at a distance because it defies our everyday intuition. But what if this spookiness isn't magic, just physics playing out in dimensions we can't see? Imagine two ants crawling on opposite ends of a folded piece of paper. To them, they're worlds apart. But if that paper bends in a higher dimension, bringing their positions close together, a whisper from one ant could reach the other instantly. In the same way, entangled particles might not be signaling faster than light through our three-dimensional space. They could be touching through a hidden fourth or fifth dimension, curled up like the paper's fold. This wouldn't break relativity's speed limit because the information isn't traveling across our universe. It's taking a shortcut through a dimension we can't perceive. This idea gets even wilder when you consider the holographic principle, which suggests our three-dimensional reality might just be a projection from a two-dimensional surface at the edge of the universe. Think of it like a movie screen. The images look three-dimensional, but they're actually encoded in flat pixels. If this principle holds, then every event in our 3D world, every collision of particles, every flicker of starlight could be rewritten as data on a distant 2D boundary. Entanglement might simply be pixels on this cosmic screen interacting in ways that only look mysterious from our limited perspective. String theory takes this further, proposing that the strings vibrating in extra dimensions could be the threads stitching this hologram together. Just as a tapestry's pattern emerges from thousands of tiny stitches, the universe's complexity might arise from strings wriggling in higher dimensional space. Entangled particles, they might share a single string stretched across hidden dimensions, vibrating in sync no matter how far apart they seem in our 3D view. The implications are staggering. If entanglement truly relies on extra dimensions, it could mean the quantum world and the cosmos are far more deeply connected than we thought. Black holes, for instance, might store information on their 2D event horizons while projecting a 3D illusion of their interior, a holographic trick that could resolve long-standing paradoxes about what happens inside them. Even time itself might emerge from these entangled threads, like a movie's narrative unfolding frame by frame. Skeptics argue these ideas are untestable science fiction dressed in equations. But experiments are already probing the edges of possibility. Quantum computers exploit entanglement to perform calculations, and gravitational wave detectors hunt for echoes of higher dimensions in the ripples of colliding black holes. Each discovery, each anomaly, could be a clue pointing toward the true architecture of reality, one where the spooky, the holographic, and the hidden dimensions are all part of the same grand design. Whether these theories hold up or not, they reveal a profound truth. The universe is far stranger than it appears. What we call reality might just be the surface of something infinitely deeper, a cosmic code written in dimensions beyond our sight, waiting to be deciphered. Gravity is the force that keeps planets in orbit and galaxies from flying apart, yet at the atomic scale, it's shockingly feeble. A tiny refrigerator magnet can defy Earth's entire gravitational pull, lifting a paperclip with ease. Why is nature's most familiar force so weak compared to electromagnetism or the nuclear forces? The answer might lie in dimensions we can't see. Picture gravity as a cup of water poured onto a sponge. Most soaks into the sponge our familiar three-dimensional space, but some drips through hidden crevices beneath. If gravity behaves similarly, leaking into extra dimensions curled up at microscopic scales, it would explain why it feels so diluted in our everyday experience. The full strength of gravity isn't missing, it's just spread thin across realities we can't perceive. This idea tackles one of physics' biggest puzzles, the hierarchy problem. The other fundamental forces are astronomically stronger than gravity. Electromagnetism, for example, is 10 to the power of 36 times more powerful. That's a 1 followed by 36 zeros. Such an extreme imbalance seems arbitrary unless there's a hidden mechanism at work. String theory suggests that mechanism could be compactified dimensions tiny, curled up spaces where gravity's influence disperses. Think of it like sound in a concert hall. If you're standing next to a speaker, the music blares loudly. But if the hall has unseen alcoves, some sound waves escape into them, leaving the main space quieter. Similarly, if gravity's waves ripple into extra dimensions, what we experience in our 3D world would be just a faint echo of its true strength. The math behind this is elegant. In some string theory models, gravity's weakness isn't a flaw, it's a clue. The equations suggest that while particles like electrons and quarks are stuck to our 3D brane, gravitons, the hypothetical carriers of gravity could slip into the higher dimensional bulk. This would make gravity seem weaker here because its effects are shared across multiple dimensions. Experiments are hunting for traces of this leakage. If extra dimensions exist, they could subtly alter gravity's behavior at tiny scales. Scientists use exquisitely sensitive devices like torsion balances, essentially ultra-precise scales, to measure gravitational forces between microscopic objects. Any deviation from Newton's inverse square law might hint at gravity spilling into unseen dimensions. So far, no definitive signal has emerged, but the search has only scratched the surface of possible dimensional geometries. Critics argue that extra dimensions are an elaborate fix for a problem that might have other solutions. Yet the beauty of this idea is how it ties together two seemingly unrelated mysteries: gravity's weakness and the universe's hidden architecture. Whether the proof comes from a lab experiment or the aftermath of a black hole collision, one thing's certain: gravity's frailty might be the very thread that leads us to the fabric of higher dimensions. If string theory's extra dimensions are real, they're not just random, crumpled spaces, they're exquisitely sculpted into shapes called calabi-yau manifolds, 6-dimensional geometric masterpieces that could determine everything from the mass of an electron to the very fabric of spacetime. Picture a snowflake's intricate symmetry, but magnified into a hyperdimensional labyrinth where every twist and curve dictates how strings vibrate and thus what particles emerge in our universe. These shapes are so complex that even mathematicians struggle to visualize them fully, often relying on 3D projections or artistic renderings to grasp their shadowy outlines. The magic of calabi-yau manifolds lies in their geometry. Just as the shape of a drum defines its sound, the contours of these hidden dimensions determine the notes strings can play, each vibration corresponding to a different particle. A slightly more stretched curve might produce an up quark, while a tighter kink could manifest as a photon. It's like a cosmic tuning system. Tweak the calabi-yau's form, and you'd rewrite the universe's entire particle catalog. Some versions might not even allow atoms to form, rendering life impossible. Ours, it seems, is a Goldilocks shape exactly tuned for existence. To understand why these manifolds matter, think of them as the hidden wiring behind reality's stage. In our everyday world, gravity and light behave differently because their forces arise from distinct vibrational patterns of strings. But zoom out into the full 10-dimensional space of string theory, and those differences blur. The calabi-yau's geometry filters the vibrations, sorting them into the forces and particles we recognize. For example, if a string's vibration loops around a tiny, twisted corridor of the manifold, it might emerge as an electron. Another threading through a wider channel could become a neutrino. The manifold isn't just housing extra dimensions, it's actively shaping physics. visualizing these structures pushes the limits of imagination. Modern researchers use 3D printed models or animations to explore their topology, slicing through higher dimensional projections like a surgeon dissecting layers of tissue. One famous analogy compares calabi-yau shapes to a multi-dimensional Swiss cheese. The holes and tunnels define how strings move, interact, and even tangle to create entanglements, spooky connections. Some theories suggest dark matter could be particles whose strings vibrate in hidden pockets of the manifold, forever just out of reach. Yet for all their elegance, calabi-yau manifolds raise thorny questions. Why this particular geometry? The math allows countless variations, 10 to the power of 500 possible shapes, a number so vast it dwarfs the atoms in the observable universe. Some physicists argue this landscape of possibilities implies a multiverse, where each version of reality sports its own unique calabi-yau configuration. Others see it as a flaw, a sign that string theory needs refinement. Either way, these enigmatic shapes remind us that the universe's deepest truths might be written not in particles or forces, but in the silent, twisting geometry of dimensions we've yet to see. Dark matter is one of the universe's most frustrating mysteries, invisible, elusive, yet making up nearly 85% of all matter in existence. We know it's there because galaxies spin faster than they should, and light bends in ways that visible matter alone can't explain. But if it's everywhere, why can't we detect it directly? The answer might not be in our instruments, it might be in our dimensions. Imagine dark matter as smoke drifting through a screen door. The smoke isn't part of the door's structure, but it can still pass through, unseen and unfelt. Now replace the door with our three-dimensional universe, and the smoke with particles moving through hidden dimensions, particles that only interact with us via gravity, the one force capable of crossing dimensional boundaries. This isn't just speculation. Some string theory models suggest dark matter could be ordinary matter, just stuck to a parallel brane floating mere millimeters away in the higher dimensional bulk. To us, it's ghostly. To the particles themselves, they're just going about their business in their own slice of reality. Think of it like two ships sailing side by side on calm waters. From each deck, you'd never see the other ship's crew, just faint ripples from their movements. If dark matter exists on a neighboring brane, its gravity would still tug at our universe, warping galaxies and bending starlight, while its particles remain forever out of reach. This would explain why decades of experiments hunting for dark matter particles, like WIMP or actions, have come up empty. We might be searching for shadows in the wrong dimension. The math behind this idea is compelling. In certain brane world scenarios, gravity bleeds into our universe from higher dimensions, while other forces stay confined to their home branes. Dark matter could be a particle that, like gravity, leaks through, but just barely, leaving only faint gravitational footprints. Some theorists even propose that supermassive black holes act as anchors, their immense gravity creating dimples in space-time that tether nearby branes together, amplifying dark matter's influence without allowing direct interaction. Could we ever prove this? The answer might lie in the cosmic microwave background, the afterglow of the Big Bang. Tiny anomalies in its pattern could hint at gravitational echoes from collisions between our brane and another. Or consider gravitational waves. If a ripple passed through an extra dimension, it might arrive at Earth slightly distorted, like a voice echoing down a hallway. Experiments like LISA, the upcoming space-based gravitational wave observatory, might one day catch these whispers from the bulk. The implications are staggering. If dark matter truly resides in extra dimensions, it would mean our universe is just one layer in a vast, multidimensional tapestry, a tapestry where most of reality is hidden in plain sight. Every galaxy, every star, every speck of dust we see might be accompanied by an invisible counterpart, dancing to the tune of dimensions we're only beginning to imagine. The hunt for dark matter isn't just about finding missing mass. it's about uncovering the hidden architecture of existence itself. We think of time as an unstoppable river flowing forward with no way to turn back, but what if time isn't just a dimension we're stuck in? What if it's more like a road with hidden detours and shortcuts woven into the fabric of higher dimensional space? In Einstein's theory of relativity, time is already the fourth dimension, as real and malleable as length or width. But string theory takes this further, suggesting that time might not just be a dimension we experience, it could be one we navigate. The key lies in the mind-bending concept of closed time-like curves paths through space-time that loop back on themselves, creating a bridge between the past and future. Picture a train track circling a mountain. If the track bends tightly enough, the train could return to the same point in space and time. In theory, this isn't just fantasy. Certain solutions to Einstein's equations, like the Gödel metric or rotating black holes, allow for such loops. But string theory adds a tantalizing twist. These curves might be stabilized or even created by the vibrations of strings in extra dimensions. Imagine space-time as a crumpled piece of paper. From our limited 3D perspective, time seems linear. But if you could perceive higher dimensions, you might see folds where distant moments touch, like 2 points on the paper pressed together by an unseen hand. These folds could act as wormholes, shortcuts through time as well as space. The catch: to traverse them, you'd need to harness energies or materials beyond our current reach, like exotic matter with negative energy to prop the wormhole open. This isn't just speculation. Physicists like Kip Thorne have shown that stable wormholes, while wildly impractical, don't violate the laws of physics as long as you can balance their immense gravitational forces. String theory offers a potential workaround. If extra dimensions exist, they might provide the scaffolding to stabilize these structures. Some models suggest that strings vibrating in calabi-yau manifolds could generate the precise conditions needed to thread a wormhole without it collapsing. But the implications are thorny. If time travel were possible, even in theory, it would rewrite our understanding of causality. Paradoxes lurk at every turn, like the infamous grandfather paradox, where changing the past erases your own existence. Some physicists argue these paradoxes are nature's way of preventing time travel, while others propose self-consistent loops where events are fixed, like a movie where the ending already accounts for any time tampering. The most radical idea, that time itself is an emergent property, a side effect of deeper processes in higher dimensions. Just as heat isn't a substance but the motion of molecules, time might be the macroscopic ripple of strings vibrating across branes. If true, mastering these vibrations could unlock control over time's flow, not by breaking physics, but by understanding its hidden architecture. For now, these ideas remain in the realm of theory and speculation. Yet they force us to confront a profound question. Is time truly the unyielding force we perceive, or just one thread in a multidimensional tapestry we've barely begun to unravel? The answer might lie not in the ticking of clocks, but in the silent hum of strings dancing through dimensions we can't yet see. Black holes aren't just cosmic vacuum cleaners. They might be the universe's best-kept secret, hiding gateways to other dimensions. At their hearts, where gravity crushes matter into oblivion, Einstein's equations hint at something bizarre. Wormholes or Einstein-Rosen bridges threading through space-time like tunnels through a mountain. Picture a black hole's singularity not as a dead end, but as a cosmic turnstile, twisting space-time so tightly that it might connect to another universe, another brane, or even another time. These theoretical bridges arise from Einstein's general relativity. When a dying star collapses into a black hole, calculations suggest its singularity could stretch space-time like taffy, pinching it into a tunnel that opens elsewhere, perhaps near another black hole's mouth or in a parallel universe. It's like folding a piece of paper so two dots touch. The wormhole is the shortcut between them. String theory takes this further, proposing that these tunnels might be lined with vibrating strings, their energy stabilizing the passage long enough for something or someone to traverse it. But there's a catch. The moment anything enters a black hole, it confronts the firewall paradox, a wall of searing radiation at the event horizon, theorized to incinerate matter before it reaches the singularity. This paradox pits quantum mechanics against relativity. Quantum rules say information can't be destroyed, yet relativity suggests anything crossing the event horizon is lost forever. If black holes do erase information, it would unravel the foundations of physics. String theory offers a lifeline. If black holes aren't just pits but holograms, their information encoded on a 2D surface at the horizon, then nothing truly enters the black hole. Instead, matter might be scrambled onto this surface like data on a hard drive, preserved but scrambled. The firewall, just an illusion, a glitch in how we perceive the transfer. Think of it like burning a book. The words seem lost, but if every letter were secretly imprinted on the ashes, the information still exists, just in a form we can't yet read. Even wilder, some string theorists propose that black holes aren't endpoints at all, but bridges to baby universes budding off our own. Imagine blowing a bubblegum bubble so big it pinches off the black hole's singularity could be the stem, inflating a whole new cosmos with its own laws of physics. Our universe might even be the offspring of a black hole in another reality, a cosmic matryoshka doll of hidden dimensions. The implications are dizzying. If black holes truly link to other dimensions, they could be nature's ultimate portals, not just for matter but for the fundamental codes of reality. The catch: no human or probe could survive the trip, at least not yet. Until we crack the firewall paradox or harness the power of strings, these cosmic gateways remain locked. But every gravitational wave detected, every quantum bit entangled, brings us closer to unraveling the mystery, and perhaps one day peering through the veil into the universe's deepest secrets. What if everything you see, the stars, your hands, even this very screen, is nothing more than a shimmering illusion, a cosmic mirage projected from the edge of reality? This isn't the plot of a sci-fi movie, it's the holographic principle, a radical idea suggesting our three-dimensional universe might be encoded on a two-dimensional surface, like a movie playing on an infinite celestial projector. At first glance, it sounds absurd, but when you dig into the math, something astonishing happens. Black holes, quantum mechanics, and even string theory's most elusive equations start clicking into place like pieces of a puzzle we didn't know we were solving. Take a hologram you'd see on a credit card, shine light on it, and a 3D image pops out, even though the data is stored on a flat 2D surface. Now imagine the entire universe works the same way. Every galaxy, every atom, every fleeting thought could be nothing more than pixels on a vast, distant boundary, a cosmic hard drive storing reality's code. The holographic principle emerged from a shocking discovery about black holes. When matter falls in, it seemingly vanishes, violating quantum mechanics' rule that information can't be destroyed. But in the 1990s, physicist Leonard Susskind proposed a solution. The information isn't lost, it's smeared across the black hole's event horizon, the 2D surface where light can no longer escape. String theory turbocharges this idea with something called AD/CFT correspondence, a mathematical bridge between gravity in a warped higher dimensional space and a quantum field theory on its lower dimensional boundary. It's like realizing the dance of shadows on a cave wall isn't random, it's a perfect translation of a richer, unseen world outside. In this framework, the strings vibrating in extra dimensions could be the source code, while our 3D reality is the rendered output. The wildest part, we might be able to test this. Quantum computers like Google's Sycamore processor are being used to simulate holographic universes in miniature. By entangling qubits, the quantum equivalent of bits, researchers can mimic how information might encode between dimensions. early experiments already show eerie parallels. Entangled particles behave as if they're linked by hidden, lower-dimensional rules, just as holography predicts. But if this is true, it reshapes everything. Your sense of touch, the taste of coffee, the vastness of the night sky, all could be data on a boundary we'll never see. Even time might be an emergent property, a side effect of how that data processes. The holographic universe doesn't diminish reality. It reveals a deeper layer of connection, where every quark and quasar is part of a grand cosmic projection. And somewhere in the interplay of strings and dimensions, the true nature of existence might be waiting not in the world we see, but in the hidden code we're just beginning to decipher. At the frontiers of particle physics, scientists are chasing ghosts, not the spectral kind, but particles and forces that flicker at the edge of detection before vanishing into uncertainty. Among these phantoms is the tantalizing hint of a fifth fundamental force, something beyond gravity, electromagnetism, and the strong and weak nuclear forces. The evidence: tiny discrepancies in how particles behave during experiments, anomalies so small they could be errors, or cracks in the Standard Model's foundation, revealing a hidden layer of reality. Take sterile neutrinos, for example. These hypothetical particles don't interact with any known force except gravity, making them nearly invisible to our detectors. They're like whispers in a crowded room, inaudible yet undeniable if you know where to listen. Experiments like Mini BUNI at Fermilab have spotted unexplained neutrino oscillations, shifts in particle types that shouldn't happen unless sterile neutrinos exist. What's eerie is that if they're real, they might not just be passing through our universe, they could be drifting through extra dimensions, only occasionally brushing up against our reality like shadows against a wall. This is where the fifth force comes in. If sterile neutrinos are sliding through higher dimensions, they might be feeling the tug of a force we've never seen, one mediated by particles that don't belong to our universe's rulebook. Think of it like this: if the known forces are instruments in an orchestra, this fifth force could be playing a different melody entirely, in a frequency only detectable if you're listening from another dimension. Some theories suggest it could be a manifestation of gravity's hidden strength in these curled-up spaces, leaking into our world as faint, unexplained nudges in particle collisions. The hunt for this force isn't just about filling gaps in equations. It could redefine how we understand dark matter, quantum entanglement, even the birth of the cosmos. At CERN, physicists are scouring proton collisions for energy that seems to vanish, not into nothingness but possibly into extra dimensions. Meanwhile, ultra-sensitive lab experiments measure how subatomic particles twist in magnetic fields, searching for deviations that might betray an unseen force's influence. Critics argue these anomalies could be statistical flukes or measurement errors, but supporters counter that history's greatest breakthroughs often started with tiny inconsistencies, like Mercury's wobbling orbit, which hinted at Einstein's relativity. Whether the fifth force is real or not, its possibility reminds us that the universe's deepest secrets might not lie in what we see, but in the dimensions we've yet to explore. And somewhere in those hidden folds, the laws of physics could be rewriting themselves. Deep within the cosmic background radiation, where whispers from the birth of the universe still echo, there may be traces of something extraordinary: cosmic strings, relics so thin yet unimaginably dense that they could be the fossilized vibrations of the Big Bang itself. These aren't the strings of string theory, but they're gargantuan cousins, one-dimensional scars in space-time, formed when the universe transitioned from a boiling soup of pure energy into the structured reality we know today. Picture a frozen lake cracking as temperatures drop, creating jagged fault lines in the ice. In the same way as the early universe cooled, symmetries in its fundamental forces broke, potentially leaving behind these cosmic cracks, strings as narrow as a proton but stretching across galaxies, vibrating with the energy of 1,000 suns. What makes cosmic strings so tantalizing is their gravitational footprint. Unlike black holes or neutron stars, which warp spacetime in predictable ways, these filaments would oscillate, kink, and snap, sending out ripples, gravitational waves with a unique signature. Imagine plucking a guitar string in a silent room. The vibrations spread outward, bending the air. Now scale that up to cosmic proportions, a string billions of light years long snapping under its own tension, sending gravitational shockwaves through the fabric of the universe. Detectors like LIGO and future observatories like LISA are tuned to listen for these bursts, which would sound like sharp pops amid the background hum of merging black holes. The connection to string theory lies in their shared origins. Just as superstrings vibrate in hidden dimensions to create particles, cosmic strings might be their macroscopic shadows, evidence that the universe's fundamental fabric once quivered with similar symmetries. Some models even suggest these strings could bridge branes, acting as cosmic zippers between parallel universes. Their detection wouldn't just confirm a wild prediction from quantum field theory. It could provide the first indirect evidence that string theory's mathematical elegance mirrors physical reality. Yet finding them won't be easy. Cosmic strings are elusive, and their gravitational waves would be faint compared to cataclysmic events like neutron star collisions. But there's another clue. Light from distant quasars, bent by a string's immense gravity, could appear duplicated in telescopes, a celestial mirage revealing an invisible thread slicing through space. Even more intriguing, if strings exist, they might have seeded the universe's large-scale structure, guiding galaxies into the vast web we see today. For now, cosmic strings remain hypothetical, but their potential discovery would rewrite cosmology. They're the universe's oldest scars, a testament to the violent beauty of creation, and possibly our best shot at glimpsing the hidden symmetries that shaped everything. Supersymmetry is one of the most elegant ideas in physics, a cosmic balancing act where every particle we know has a hidden, heavier twin. Electrons would have selectrons, quarks would have squarks, and even the photon would have a photino. At first glance, this seems like overkill, but these sparticles could solve some of the universe's biggest riddles, from the nature of dark matter to why gravity is so weak. And when you tie supersymmetry to string theory's extra dimensions, things get even more interesting. Think of supersymmetry as a mirror, reflecting our known particles into a shadow world where matter and forces blur together. In this mirror universe, fermions, the building blocks of matter like electrons and quarks, pair up with bosons, the force carriers like photons and gluons. This symmetry isn't just poetic, it's a mathematical lifeline for string theory. Without supersymmetry, the equations underpinning string theory spiral into chaos, producing nonsense like infinite energies or imaginary particles. Sussy tames those wild calculations, acting like a cosmic accountant that ensures every vibration, every interaction, stays balanced across all those hidden dimensions. But here's the catch: if sparticles exist, where are they? The Large Hadron Collider has hunted for them for years, smashing protons together at near light speed, yet no squarks or photinos have shown up. This missing partner puzzle has led some to declare supersymmetry dead, but others argue we're just looking in the wrong way. Imagine tuning a radio. If you're slightly off the station's frequency, all you hear is static. Similarly, sparticles might be far heavier than we predicted, their signals drowned out by background noise. Or worse, they might decay almost instantly into ordinary particles, leaving only faint fingerprints in collision data. One compelling idea is that sparticles aren't missing, they're hiding in plain sight. If extra dimensions are real, some sparticles could be much lighter than expected, their mass diluted by vibrations in higher dimensional space. In certain string theory models, gravitinos, the superpartners of gravitons, might leak into our universe as ultra-light dark matter, invisible yet shaping galaxies with their gravity. Others propose that sparticles could be tucked into the folded geometry of calabi-yau manifolds, only detectable through gravitational anomalies or subtle quantum effects. The stakes couldn't be higher. If supersymmetry is real, it would mean nature operates on a grander symmetry than we ever imagined, one that connects particles, forces, and hidden dimensions into a single harmonious framework. It could explain why the Higgs boson is so oddly light, why dark matter outnumbers visible matter 5 to 1, even why the universe didn't tear itself apart moments after the Big Bang. But if particles remain elusive, physicists might need to rewrite not just supersymmetry but the very foundations of string theory. For now, the hunt continues. Upgraded colliders, deeper underground detectors, and even quantum computers are joining the search. Whether supersymmetry is confirmed or overturned, its legacy is already profound. It's pushed us to question whether the universe's deepest truths are hiding not just in particles we can see, but in the silent echoes of dimensions we've yet to explore. The universe seems eerily fine-tuned for life. Gravity is just strong enough to hold planets together but weak enough to let stars form. The nuclear force is perfectly balanced for atoms to exist. But here's the really peculiar part. Our three spatial dimensions feel necessary. If we had just two, complex life couldn't navigate. With four or more, gravity's pull would weaken so drastically that stars and planets might never coalesce. It's as if the cosmos hit a cosmic jackpot, a Goldilocks zone of dimensionality where everything aligns for life to emerge. This uncanny precision is what physicists call the anthropic principle, the idea that the universe's fundamental constants, including its number of dimensions, appear tailored for observers because, well, we're here to notice them. But is this fine-tuning evidence of design or just a statistical fluke? Think of it like a puddle marveling at how perfectly its hole fits its shape. The puddle doesn't realize there are countless other holes out there, most empty, a few with water. Similarly, our universe might be one of countless variations in a multiverse, each with different dimensions and physical laws. In most, conditions are too chaotic or sterile for life, but in rare pockets like ours, the dice roll just right: three stable dimensions, balanced forces allowing galaxies, planets, and eventually curious minds to ponder why things seem so perfect. String theory's landscape of possible calabi-yau manifolds supports this idea. With 10 to the power of 500 potential shapes for extra dimensions, the multiverse could be a vast tapestry of realities, each with its own unique geometry. Most might crumple instantly or spawn only fleeting particles. Ours, by sheer chance, stabilized into a configuration where strings vibrate in ways that generate stable matter and life-friendly physics. It's not that the universe chose three dimensions for us, it's that we exist in one of the vanishingly few where three dimensions allowed us to be. Critics argue this explanation is a cop-out, a way to avoid deeper questions about why the universe is the way it is. But proponents counter that it's no different from accepting Earth's position in the habitable zone around the Sun. We don't invoke divine intervention to explain why we're not on a frozen rock near Pluto or a scorched world next to Mercury. The multiverse simply scales this logic up, framing our universes, fine-tuning as a selection effect. We're here because this is one of the rare places we could be. Yet the debate rages on. Some theorists propose an even wilder twist. What if life could adapt to other dimensional realities? Two-dimensional beings might develop entirely different forms of intelligence, while higher dimensional life could perceive time and causality in ways we can't fathom. Our three dimensions might feel just right, not because they're the only possible stage for life, but because they're the only stage we can recognize. The anthropic principle doesn't answer everything, but it sharpens the question. Is our universe's dimensionality a happy accident, a statistical inevitability in an infinite multiverse, or something else entirely? The answer might lie not in the dimensions we see, but in the ones we don't, the hidden folds of reality where the true nature of existence could be written. When we hear about UFOs darting across the sky with physics-defying maneuvers, It's easy to dismiss them as extraterrestrial spacecraft, but what if they're not visitors from across the stars, but from next door in a dimension we can't perceive? The idea sounds ripped from a sci-fi novel, yet some physicists argue it's worth considering not as proof, but as a legitimate exploration of how higher dimensional beings might interact with our world. The key lies in those hidden branes from string theory. If parallel universes exist mere millimeters away in the bulk, separated by dimensions we're blind to, could advanced civilizations there have found a way to reach across and briefly enter our reality? Imagine standing in front of a waterfall. You see only the rushing water, not the fish beneath the surface unless one leaps out for a split second before disappearing again. To the fish, the air above is an alien realm. Now flip the analogy. If our universe is a three-dimensional waterfall, beings from a higher dimensional brane might have the ability to dip into our space, appearing as fleeting, inexplicable phenomena before vanishing without a trace. Their technology wouldn't need to break our laws of physics. They'd simply be leveraging geometries we can't fathom. This isn't to say every UFO sighting is an interdimensional tourist. The vast majority have prosaic explanations: drones, atmospheric phenomena, even secret military tech. But a handful of cases defy easy categorization, like the infamous Nimitz encounters, where pilots described objects accelerating instantly or moving as if unbound by inertia. Could these be glimpses of something breaching the brain barrier? Even the Pentagon's UAP task force has entertained the possibility, with former intelligence official Luis Elizondo openly speculating about adjacent dimensions in interviews. The math offers intriguing, if speculative, support. In certain brain world models, collisions or ripples between parallel membranes could create temporary bridges, wormholes, or cosmic strings threading through the bulk. A civilization mastering such structures might navigate them like cosmic highways, appearing and disappearing at will. Some theorists even suggest dark matter could be the gravitational anchor holding these passages open, explaining why UFOs are often reported near nuclear facilities or fault lines, areas where spacetime itself might be subtly warped. Skeptics rightly point out the lack of concrete evidence. Extraordinary claims require extraordinary proof, and so far, no interdimensional beings have left a manual on our doorstep. But the scientific method isn't about dismissing ideas, it's about testing them. Projects like Harvard's Galileo initiative aim to analyze UFO reports with rigorous astrophysical tools, searching for anomalies that might hint at non-human intelligence, whether extraterrestrial or other. At its core, this isn't about proving aliens exist. It's about recognizing that the universe's strangeness might exceed our current frameworks. If history teaches us anything, it's that today's crackpot theory can become tomorrow's paradigm after all. Einstein's curved spacetime was once laughed at, and black holes were pure mathematical fantasy until we photographed one. Whether UFOs are interdimensional or not, they remind us that the cosmos still holds mysteries begging for exploration. And somewhere in the collision of science and speculation, we might just find clues to the greatest question of all. Are we alone, or is reality far more crowded and far weirder than we ever dared dream? The Large Hadron Collider isn't just smashing protons to uncover known particles, it's hunting for something far more exotic. Miniature black holes, fleeting specks of spacetime curvature that could vanish in a blink, leaving behind only a whisper of radiation. If detected, these microscopic monsters wouldn't just confirm Hawking's famous prediction, they'd be a smoking gun for extra dimensions. Here's how it works. When protons collide at nearly the speed of light, the energy packed into that tiny impact could, theoretically, warp spacetime enough to create a black hole smaller than an atom. But in our familiar three-dimensional universe, the energies required are impossibly high, trillions of times beyond what the LHC can muster. That's where extra dimensions come in. If gravity can seep into hidden dimensions, as string theory suggests, its true strength might be concentrated in those unseen folds. This would lower the energy threshold for black hole formation, bringing it within reach of our colliders. Imagine trying to push a needle through a single sheet of paper. It's tough, but stack 100 sheets together and the needle slides through easily. Extra dimensions could act like that stack, making space-time more pierceable than we ever imagined. The catch: these black holes wouldn't last. According to Hawking radiation, tiny black holes should evaporate almost instantly, exploding into a burst of particles and energy. Detectors at the LHC are tuned to spot these telltale showers. A sudden, symmetric spray of high-energy debris with no obvious source. It's like finding a puddle in the desert with no rain clouds in sight, evidence of something extraordinary. So why haven't we seen them yet? One possibility is that extra dimensions are even smaller or more tightly curled than predicted, pushing the energy needed beyond our current limits. Another is that black holes decay too quickly, leaving no trace for our instruments to catch. Or perhaps the strings that form them vibrate in ways that make black holes rarer than expected. There's also a chance we're misinterpreting the data. What looks like background noise might actually contain hidden signals buried under layers of statistical uncertainty. The search isn't over. Upgrades to the LHC and future colliders, like the proposed Future Circular Collider, will probe even higher energies, tightening the net around these elusive phenomena. And while many black holes remain hypothetical, their discovery would revolutionize physics overnight, not just proving extra dimensions exist, but opening a window into the quantum nature of gravity itself. Until then, every collision is a roll of the cosmic dice, a chance to glimpse the hidden architecture of reality. For over a century, physics has been split by a cosmic divorce, general relativity, ruling the vast cosmos with its warped space-time, and quantum mechanics, governing the frenzied dance of subatomic particles. These two titans describe reality with stunning accuracy, yet their laws clash violently when pushed to extremes. At the heart of a black hole's singularity, or the first instance after the Big Bang, their equations explode into nonsense. The dream of uniting them, a theory of quantum gravity, is the Everest of modern physics, and string theory's bold proposition that hidden dimensions are the bridge. Here's the elegant problem. In Einstein's universe, gravity isn't a force but the curvature of space-time, a smooth, geometric tapestry. But zoom into quantum scales, and this tapestry frays into probabilistic chaos, where particles pop in and out of existence and empty space boils with virtual particles. Gravity, stubbornly weak, refuses to play by quantum rules. String theory resolves this by reimagining particles as vibrating strings, not point-like dots but tiny loops wriggling in higher dimensional space. These strings don't just move through dimensions, they need them to vibrate in patterns that manifest as gravity, photons, and everything in between. It's like realizing a piano's rich sound doesn't come from the keys alone, but from the instrument's hollow body amplifying their vibrations. But string theory isn't the only contender in this unification quest. Loop quantum gravity takes a starkly different approach. Instead of adding dimensions, it quantizes space-time itself, breaking it into tiny, indivisible chunks. Think of the universe as a mosaic of interlocking atoms of space. Picture a pixelated video game world versus string theory's symphonic hologram. Neither has definitive proof yet, but their contrasts are revealing. Loop quantum gravity thrives in our familiar 4 dimensions, weaving gravity from the fabric of space-time's quantum knots. String theory, meanwhile, embraces higher dimensions as essential scaffolding, their geometry dictating how strings harmonize. The stakes couldn't be higher. If string theory's extra dimensions are real, they'd explain why gravity fades to a whisper at small scales, its strength diluted across unseen folds. The LHC's hunt for miniature black holes hinges on this. If they form at lower energies than expected, It could mean gravity's true force is concentrated in dimensions beyond our perception. Loop quantum gravity counters that simplicity is key. Why invoke unseen dimensions when space-time's granularity might suffice? Yet both theories share a tantalizing hint. Their math converges near black holes where entropy, a measure of disorder, can be calculated identically from either approach. It's as if two hikers scaling opposite sides of a mountain glimpse the same valley below, suggesting a hidden unity. Whether that valley is built from strings, loops, or something stranger remains unknown. But the quest itself reveals a profound truth. The universe's deepest secrets might not live in the dimensions we see, but in the invisible stitches sewing them together. Wormholes aren't just sci-fi plot devices, they're legitimate predictions of Einstein's equations, cosmic tunnels that could connect distant points in space-time or even bridge separate universes. In string theory, these shortcuts take on a whole new dimension literally. Imagine folding a sheet of paper so two distant dots touch. A wormhole is the hypothetical tunnel piercing through the fold, a shortcut bypassing the usual rules of distance. But here's the catch. According to classical physics, these tunnels would collapse instantly, crushed by their own gravity before anything could pass through. That's where string theory's hidden dimensions and exotic materials might rewrite the rules. At the heart of this puzzle is the delicate balance needed to keep a wormhole open. Picture a tunnel dug through sand without supports. The walls cave in immediately. Wormholes face the same problem, but their supports would need to defy gravity's crushing force. Enter exotic matter, a theoretical substance with negative energy capable of repelling gravity rather than attracting it. In string theory, such material might arise from the vibrations of strings in higher dimensions. Certain configurations of calabi-yau manifolds, those intricate six-dimensional shapes, could produce particles with negative mass, essentially cosmic scaffolding to prop open a wormhole's throat long enough for something to traverse it. But even with exotic matter, stability isn't guaranteed. Quantum fluctuations, tiny, unpredictable shifts in energy, could destabilize the wormhole, snapping it shut like a rubber band. Some models suggest that strings threading through the wormhole's structure might counteract this, their vibrations acting like tension wires to reinforce the tunnel. Think of it like a suspension bridge. The string's energy could provide the counterbalancing force needed to keep the wormhole from collapsing under its own weight. The wildest possibility, wormholes might not just connect points in our universe, they could link entirely separate branes floating in the higher dimensional bulk. If two branes momentarily brushed against each other, their interaction could stitch a temporary wormhole between them, a fleeting doorway between realities. This wouldn't just be a shortcut through space, it could be a bridge between worlds with entirely different physical laws. The practical hurdles are staggering. Even if wormholes exist, navigating them would require energies and technologies far beyond our grasp. Assuming we could survive the tidal forces, radiation, and potential time dilation effects. But the theoretical implications are profound. Wormholes could offer a way to test string theory's predictions, from the existence of extra dimensions to the nature of dark energy. And if they're out there, whether as cosmic flukes or artifacts of an advanced civilization, they'd redefine our place in the cosmos not just as inhabitants of a single universe, but as potential travelers in a vast, multidimensional network of hidden pathways. String theory's greatest strength might also be its most frustrating weakness. The math is so breathtakingly elegant that it predicts nearly everything, and therefore almost nothing. Imagine designing a master key that could open every lock in the universe, only to realize you have no way to prove which lock it actually fits. That's the paradox haunting string theory. For all its mathematical beauty, it's been mocked as not even wrong, a phrase coined by physicist Wolfgang Pauli to describe ideas so vague they can't be falsified. The heart of the issue, those extra dimensions, If they're curled up smaller than an atom or tucked away on distant branes, how could we ever detect them directly? Take the Large Hadron Collider. It was built to smash particles at energies that might reveal supersymmetry or miniature black holes, key predictions of string theory. Yet after years of collisions, no squarks or hidden dimensions have shown up. Skeptics argue this silence is damning. If the theory requires energies a quadrillion times higher than the LHC can muster, it's effectively untestable with current technology. Even worse, some versions of string theory allow for 10 to the power of 500 possible configurations of extra dimensions, a landscape so vast that almost any observation could be retrofitted to match it. Critics compare it to a chef claiming their recipe explains all possible meals, even if you never taste the dish. But is the criticism entirely fair? History is littered with theories that seemed untestable until someone invented the right tool. Neutrinos were once purely hypothetical, now we detect them by the trillions. Black holes were mathematical curiosities until we photographed one. String theorists argue we're in a similar pre-breakthrough limbo. Future experiments might not see extra dimensions directly, but they could uncover indirect fingerprints like deviations in gravity at microscopic scales or anomalies in quantum entanglement that hint at higher dimensional threads stitching reality together. The debate gets fiercer when competing theories enter the ring. Loop quantum gravity, for instance, rejects extra dimensions entirely, proposing instead that space-time is woven from tiny, indivisible loops. It's a radical alternative that, unlike string theory, makes concrete predictions about quantum black holes and the Big Bang. Yet it has its own challenges, like explaining how smooth space-time emerges from these discrete chunks. Meanwhile, emergent gravity theories suggest gravity isn't fundamental at all, but an illusion created by deeper quantum effects, an idea that, if proven, would upend string theory's core premise. Philosophically, the fight boils down to a question: should a theory's beauty and internal consistency count as evidence if we can't test it? Einstein's general relativity was initially celebrated for its elegance, but its predictions like light bending around the sun were later confirmed. String theory's defenders argue its mathematical coherence is a clue we shouldn't ignore, even if proof lags decades behind. Detractors counter that science thrives on falsifiability, not faith in equations. The haunting possibility: extra dimensions might forever remain mathematical ghosts, real in theory but eternally beyond our grasp. If they're locked behind energy barriers we can never breach, or if their effects are indistinguishable from randomness, string theory could stagnate as the ultimate what-if of physics. Yet even in that limbo, it's reshaped how we think. From black hole thermodynamics to the holographic principle, its ideas have spilled into other fields, proving that sometimes the quest for answers matters as much as the answers themselves. Whether string theory survives or falls, it's already stretched our imagination further than we thought possible into dimensions we may never see, but can't stop exploring. What if the Big Bang wasn't the beginning, just the latest reboot in an endless cycle of cosmic destruction and rebirth? Picture two colossal sheets of rubber drifting through a higher dimensional void. When they collide, the impact sends shockwaves rippling across their surfaces, igniting firestorms of energy and matter. That's the essence of ekpyrotic theory, a radical idea suggesting our universe might have been born from a cataclysmic collision between branes, those multidimensional membranes floating in the bulk of string theory's hidden dimensions. Instead of a singular explosion from nothingness, the Big Bang could have been a cosmic reset button, a rebound event in an infinite loop of collisions. This isn't just poetic imagery. The math reveals something startling. When branes collide, their kinetic energy converts into the seething plasma of a newborn universe. It's like smashing two cymbals together. The crash creates a symphony of vibrations, except here, the music is the birth of galaxies, stars, and eventually us. These collisions wouldn't be random accidents, but part of a rhythmic dance dictated by the geometry of the bulk. Some models even suggest that dark energy, the mysterious force accelerating the universe's expansion, could be the slow buildup of tension as branes stretch apart, priming the cosmos for its next collision billions of years from now. Cyclical cosmologies like this flip the script on time itself. Ancient Hindu texts spoke of universes breathing in and out, expanding and collapsing in vast cycles. Modern physics echoes this intuition, but with a twist. Each cycle might not erase the past entirely. Quantum information could persist through brane collisions, like a message etched into the fabric of space-time that survives the fire. Black holes, those cosmic vaults of data, might hold the key. If their information isn't destroyed but encoded on the event horizon, a concept called holography, it could theoretically transfer to the next iteration of the universe, a cosmic carryover from one cycle to the next. The echoes of these collisions might still be visible today. The cosmic microwave background, the afterglow of the Big Bang, could contain faint imprints of pre-bang physics, like bruises left by a prior universe's death throes. Some researchers hunt for anomalies in its polarization patterns or unexpected swirls in the distribution of galaxies, searching for evidence that our universe was shaped by something older. Others speculate that gravitational waves, ripples in space-time from colossal events, might carry a hidden signature of the brane collision that birthed us. Yet skeptics argue that without observable proof, ekpyrotic theory remains speculative. Why favor it over the traditional inflation model, where the universe expands exponentially from a singularity? The answer lies in elegance. Inflation solves many puzzles, like why the cosmos looks so uniform, but it relies on an ad hoc field that vanishes after doing its job. Brane collisions, by contrast, emerge naturally from string theory's geometry, offering a mechanism that doesn't require fine-tuned starting conditions. The implications are dizzying. If the universe cycles through brane collisions, time might not have an arrow at all, just an endless loop, with each iteration spawning new laws of physics, new constants, even new dimensions. Civilizations could rise and fall countless times, their history erased by the next collision, their atoms reforged into fresh stars, and somewhere in the bulk, invisible to us, other branes might harbor entirely different cosmologies, their collisions writing origin stories we'll never witness. Whether this vision holds or crumbles under scrutiny, it forces us to confront a humbling truth. The Big Bang might not be the ultimate beginning, but a single note in a symphony of universes, each born from the wreckage of the last. The question isn't just how our cosmos began, it's whether beginnings and endings are illusions, fragments of a deeper reality where dimensions collide and everything starts anew. Consciousness might be the most intimate yet mysterious experience in the universe, a silent symphony of thoughts, perceptions, and self-awareness unfolding inside your skull. But what if that symphony isn't confined to the three-dimensional theater of your brain? What if consciousness itself is tapping into dimensions beyond our perception, weaving reality from threads we can't yet see? This isn't just wild speculation, it's a frontier where physics, philosophy, and the nature of mind collide. Consider panpsychism, the radical idea that consciousness isn't exclusive to complex branes, but is a fundamental property of the universe like mass or charge. In this view, even particles might possess a flicker of subjective experience, not thoughts as we know them, but a raw, primal awareness. String theory's extra dimensions could give this idea a startling twist. If consciousness is woven into the fabric of reality, those hidden dimensions might be its loom. Think of it like radio waves. You can't see or touch them, yet they carry music, voices, data, an invisible layer of reality humming beneath the surface. Could consciousness be a higher dimensional broadcast, with our brains acting as receivers tuned to a frequency we don't yet understand? The link grows stranger when you examine quantum mechanics. Particles can exist in multiple states at once until measured when they choose one. This collapse of the wave function, as it's called, has puzzled scientists for decades. Some, like Nobel laureate Roger Penrose, suggest consciousness plays a role in this process. In his orchestrated objective reduction theory, quantum vibrations in microtubules, tiny structures inside brain cells, interact with the fabric of space-time, effectively deciding reality's outcome. Now imagine those vibrations aren't just happening in our three-dimensional neurons, but are entangled with strings oscillating in extra dimensions. Suddenly, the act of observation, of being conscious, might not just influence reality, but emerge from a deeper, multidimensional dance. Then there's the holographic principle, which posits that our 3D universe is a projection from a 2D boundary. If true, consciousness could be a hologram too, a three-dimensional experience generated from information encoded at the edge of reality. Patients who have undergone near-death experiences often report perceptions that defy spatial logic, seeing events from multiple angles at once, or feeling a union with the cosmos that transcends location. These accounts, while anecdotal, hint at a mind unbounded by ordinary geometry, as if glimpsing a higher dimensional perspective before snapping back to our limited frame. Skeptics argue these ideas stretch science beyond its limits, conflating metaphysics with testable theory. Yet the overlap is tantalizing. If higher dimensions exist, and if consciousness is somehow rooted in quantum processes that stretch across them, then our sense of self, our very thoughts, might be shadows of something vaster. It's like a flatlander trying to comprehend a sphere. Our brains, evolved for 3D survival, might lack the framework to perceive the full dimensionality of our own awareness. The implications spiral outward. Could meditation or psychedelics, which alter consciousness so dramatically, be tweaking our dimensional tuning? Some researchers speculate these states temporarily loosen the brain's usual filters, allowing glimpses into the raw, multi-layered fabric of perception. Even creativity, those flashes of insight that seem to come from nowhere, might arise from the subconscious mind sifting through a higher dimensional landscape of possibilities. Ultimately, whether consciousness is a higher dimensional phenomenon or an emergent property of complex brains remains unanswered, but the question itself reshapes how we see reality. If the mind isn't just a byproduct of neurons firing but a bridge to unseen dimensions, then exploring consciousness could be the key to unlocking the universe's deepest secrets, not through telescopes or colliders, but by turning inward toward the infinite expanse within. Imagine a civilization so advanced it doesn't just exploit the laws of physics, it rewrites them, bending dimensions like blacksmiths shaping steel. In the far future, mastering extra dimensions could unlock technologies indistinguishable from magic. Take energy. What if we could tap into the higher dimensional bulk where gravity's true strength resides? Picture a power plant not fueled by fission or sunlight, but by siphoning gravitational energy leaking from adjacent dimensions, like drilling a well into an underground river hidden beneath our feet. The energy output would dwarf anything possible in our three-dimensional confines, offering near-limitless power without the pollution of fossil fuels or the radioactive waste of nuclear reactors. Communication could undergo a similar revolution. If entangled particles share connections through higher dimensions, as some theories suggest, we might build networks where information travels instantaneously across vast distances, no lag, no signal degradation. It's like two people whispering through a folded piece of paper. While outsiders hear only silence, the message arrives clear and unfiltered. Such a system wouldn't just replace the internet, it'd render interstellar delays obsolete, enabling real-time conversations with colonies on Alpha Centauri or researchers orbiting a distant pulsar. Then there's the dream of faster-than-light travel. The Alcubierre drive, a hypothetical warp engine, bends space-time to create a bubble where the ship rides a wave of compressed space ahead and expanded space behind, never breaking Einstein's speed limit locally. But here's the twist. Sustaining such a bubble requires exotic matter with negative energy, something that might naturally exist in higher dimensional geometries. String theory's calabi-yau manifolds could theoretically harbor particles with the right properties, acting as cosmic fuel for bending the fabric of reality itself. Without access to these hidden dimensions, the energy demands might be impossibly high, but with them, warping space-time could become as routine as igniting a rocket booster. Critics argue these ideas border on fantasy, yet history shows today's impossibilities are often tomorrow's blueprints. The quantum realm was once dismissed as mathematical nonsense. Now it powers our smartphones. If extra dimensions are real, the leap from theory to technology might just be a matter of time and dimensionality. The universe's greatest breakthroughs could lie not in what we see, but in what's been hiding beside us all along. Hollywood loves to bend the rules of physics for dramatic effect. Who wouldn't want to watch Matthew McConaughey surfing a wave near a black hole or Benedict Cumberbatch folding reality like origami? But while these scenes make for jaw-dropping visuals, they often blur the line between scientific possibility and pure fantasy. Take Interstellar's depiction of time dilation near Gargantua, the film's fictional black hole. The movie shows astronauts on a watery planet experiencing hours while decades pass on Earth. The physics here isn't entirely wrong. Time indeed slows near massive objects due to general relativity, but the scale is exaggerated. In reality, you'd need to orbit dangerously close to a black hole's event horizon for time to stretch that dramatically, and the tidal forces would rip apart any planet or person long before the clock slowed enough to miss a birthday back home. Then there's Doctor Strange's kaleidoscopic dimension hopping. The film portrays alternate realities as vibrant, overlapping realms where the laws of physics are mere suggestions. While string theory does propose extra dimensions, they're not psychedelic playgrounds where gravity reverses on a whim. Hidden dimensions, if they exist, would be curled up at scales smaller than an atom, their geometry dictating particle behavior in our world, not granting sorcerers the power to bend cities like rubber. The movie's mirror dimension is pure invention. Real interdimensional travel would likely involve navigating microscopic wormholes or manipulating branes in higher dimensional space, not waving your hands to fold skyscrapers. Even Contact, one of sci-fi's more grounded films, takes liberties. The wormhole transit sequence shows Jodie Foster's character tumbling through a tunnel of light, encountering visions of her past. In reality, traversing a wormhole, assuming one could be stabilized, would be utterly uneventful. No flashes of light, no existential visions. You'd simply exit somewhere else in the universe or another universe entirely without fanfare. The drama comes from the implications of the journey, not the journey itself. The common thread in these films, they prioritize spectacle over subtlety. Real theoretical physics is often stranger than fiction, just less cinematic. Time dilation near a black hole is a mind-bending concept even without Hollywood's embellishments. The true nature of extra dimensions could rewrite our understanding of reality, even if they don't glow like neon fractals. And wormholes, while mathematically plausible, would be less like roller coasters and more like cosmic shortcuts hidden in the fine print of Einstein's equations. That doesn't mean sci-fi gets it all wrong. The Matrix's simulation hypothesis aligns with some philosophical interpretations of quantum mechanics. Arrival's linguistic approach to alien communication mirrors real-world theories about language shaping perception. Even Interstellar's portrayal of a tesseract, a four-dimensional cube, as a way to navigate time is rooted in legitimate, if speculative, physics. The best sci-fi uses artistic license to point toward truth, even if it takes creative detours. The takeaway: enjoy the spectacle, but remember, the universe's real mysteries don't need CGI to be awe-inspiring. The equations scribbled on a physicist's chalkboard, the ones describing curled-up dimensions, quantum entanglement, or the birth of universes, hold a grandeur all their own. And somewhere between the wild imagination of filmmakers and the disciplined rigor of scientists, We're all just trying to make sense of this vast, multidimensional cosmos we call home. We've journeyed through a reality far stranger than fiction, where dimensions curl into hidden labyrinths, universes collide like ghostly sails in a higher dimensional sea, and the very fabric of existence hums with the vibrations of cosmic strings. These aren't just abstract ideas, they're frontiers of human curiosity, pushing the boundaries of what we thought possible. From the mind-bending math of calabi-yau manifolds to the possibility of black holes birthing new realities, every concept we've explored reveals a cosmos richer and more mysterious than our everyday senses suggest. What makes this quest so thrilling isn't just the answers, it's the questions that keep unraveling. Could dark matter be matter from another dimension? Is consciousness somehow tapping into these hidden layers? Are we, like the Flatlanders in Carl Sagan's famous analogy, mistaking our limited perception for the full scope of reality? Sagan once described us as creatures living in the flatlands of ordinary experience, unaware of the higher dimensions that silently structure our world. That's the heart of this adventure, recognizing that the universe's greatest wonders might be hiding in plain sight, woven into dimensions we're only beginning to imagine. The beauty of science is its willingness to chase the absurd until it becomes the obvious. Every revolutionary idea, from Earth orbiting the Sun to space-time bending like fabric, was once dismissed as fantasy. String theory and its multidimensional cousins might face skepticism today, but they remind us that progress begins with bold questions. What if gravity's weakness is a clue? What if the Big Bang was a cosmic rebound? What if everything we see is a hologram projected from the edge of existence? So stay curious. The next time you look at the night sky, remember, those stars might be closer than they appear, separated not by distance but by dimensions we've yet to map. The universe's greatest story is still being written, and every wild, untested idea brings us closer to reading it. As Sagan would say, somewhere, something incredible is waiting to be known. And who knows, the key to unlocking it might be hiding in a dimension just beyond your fingertips.